Today's lesson is over section 3.5, which is talking about implicit differentiation. Now, implicit differentiation is a way for us to be able to take the derivative of an equation or function that has two or more variables involved in it. Now, we're only going to be looking at it when we have two variables, mainly x and y. Now, the process doesn't have a formal definition or anything because there is no special way of writing this, but I'm going to be adding things on to when I do take the derivative to show when I'm taking the derivative with respect to x and when I'm taking the derivative with respect to y. Okay, so that's really the only thing that changes. Nothing else really differs from that because I'm still going to take derivatives using all the rules that I've already talked about in previous lessons. Okay, so for this first problem, we're trying to find the x values of the points where this equation has a tangent line of slope -1. So I first chose to rewrite my equations on the inside so it's easier to take the derivative. And so when I took the derivative of the first statement, it only has x's involved, so it's chain rule, so the 2 comes down, the derivative of the inside is 1/2, but it's with respect to x, so I put a dx there. The second one only has a y there, so I took the derivative of that same way, but then I put a dy afterwards, okay? And so that's the addition that we put on these. Then after that, for me to be able to say this is the derivative, it needs to be dy over dx. So I am in the process of manipulating this equation so that it is solved for dy over dx, so then it states the derivative. So I'm able to move the things around. So I moved the dx to one side and then divided both sides by dx and then what dy was multiplied to. And then once I have that derivative, now I want to be able to set it equal to the slope that I'm looking for, or the x values I'm looking for that slope. So I set it equal to -1, and now I'm in the process of solving. So I multiply both sides by 1/2 y plus 1, since that was in the denominator. I wanted to get rid of all the fractions, so I multiplied everything by 2, and that makes it a little easier to find that y equals x minus 3. Okay, now using that fact, I plugged that into my equation that I had at the beginning, and so I made it a little easier to solve. Now I noticed that there are 2x minus 1 divided by 2 squares, so then I kind of coupled them together and made it 2. Then from there I divided by 2 to both sides, and then I'll have to take the square root of both sides to be able to get rid of the square. That gives me a plus or minus 1 over square root of 2. You could have also rationalized that to be square root of 2 over 2. Then I multiply by 2, and that gets me 2 over root 2. But here, this is when I rationalize at this point because I don't like the looks of 1 plus or minus 2 over root 2. So I multiply both top and bottom by root 2, which gives me the same value of root 2 there. So 1 plus or minus square root of 2 is my x portion of this, and so then I use my y equals x minus 3 to help me find what the y values are in correspondence. So plugging in 1 plus square root of 2 in gets me -2 plus root 2. Plugging in 1 minus root 2 gets me -2 minus root 2. And so then I'm able to find both of my points there. And that's my answer. Okay. Example 1 here wants us kind of to do the same thing, but I want to find the equation of the tangent line for this equation at the point -6, 8. So I need to find the derivative first. So I take the derivative of x squared, which is 2x dx, and then the derivative of y squared, which is 2y dy. Derivative of 100 is 0. And then here, just like we did on the other one, I need to manipulate the equation so it's equal to dy over dx. So I move the dx over, and then to divide both sides by dx and what dy was multiplied to. So it gets me -x times or divided by y. Then I plug in -6, 8 into that. It gets me a slope of 3/4. And then using slope-intercept form, I can plug in 3/4 and my point to help me find my y-intercept. And in doing so, that allows me to find that it's 25/2. I plug it back in, and that is the equation of the tangent line. Okay, another one with the same idea behind it. Now here, you have x cubed plus y cubed, and that's very similar to x squared plus y squared. But then on the right side, we have 6xy, and so then I have to use the product rule to help me kind of divvy that up. And so take the derivative of the first, which will be just x, or x becomes 1. So that allows me to just have the 6y, but then it's still with respect to dx. And then I take the derivative of the second, which will be just 1 for the y, but so I'm left with 6x, but it's with respect to dy. And so then that's kind of how I get that one. So you're still doing product rule. It's just when you do the product rule, you need to have what you're taking the derivative with to get that. Then after that, once I've solved for dy over dx, I plug in the 3, 3 like we did in the last one. We find the slope is -1, and then we use slope-intercept form to help us find the actual line of the tangent, which gives us -1x plus 6. Okay, example 3, very similar. Don't get thrown off by the y prime. It's still asking for the same thing, just the derivative. And so I'm using the same ideas. So derivative of x squared. Now, x times y squared is a product rule. So derivative of the first times the second with respect to x. Derivative of the second times the first with respect to y. Now here, I only have one dy, so I chose to move the dy over to the right. And then from there, I can divide by -2x to both sides and divide by dx to both sides. And that gives me my answer. Okay, here there's a lot more going on. So I have product rule with the x squared times y squared. So that's how I got the first part. And then here I also have product rule, but then there's also some chain rule in there because y plus 1 is inside of a square. So taking the derivative there, 1, and then it's all with respect to y. Now notice the right side is all y's. Okay, so once I move this 2x squared y dy to the right, now I literally have everything that is with respect to the derivative of y. So I can kind of put it all together and just write 1 dy, kind of like you would factor it out. We just put it at the end rather than in the front. And then from here, I'm really just kind of trying to simplify this as best as I can. And so I'm going to multiply those first 2 parentheses. I also am going to take y plus 1 squared and simplify that out to get y squared plus 2y plus 1. And then from there, I'm looking for like terms. Also, I'm going to take the -2y and multiply it through. Okay, and then from there I can see that there's lots of like terms, so there's some y cubes, some y squareds, there are also some terms with just y. Now even though there's a -2x squared y at the end, that doesn't really go with anything, so it kind of has to sit at the end and be by itself. And then just like we've done before, I'm going to divide both sides by dx, then also divide by what's being multiplied to dy, which is a very long statement, unfortunately. And then once I've done that, now I'm able to get my final fraction. Here I also notice that everything has a common 2 involved, so I'm able to reduce out a 2, and that gives me my final answer. Okay, now for our last example here, this one's kind of tricky. So when I do this one, I'm going to write it in a little bit of a different way. So because we usually take the derivative with respect to x and not usually with y, you can kind of choose not to write the dx's if you want and just write kind of like the y primes or the derivatives of y. And so here, because I have an x, and I'm going to have to find the second derivative if you notice the directions up there. So I chose to kind of not write the dx's, but I can write y prime. And then in doing the same process, it's kind of like our dy in that sense. And so then when I solve, I'm able to say that that is the same thing as dy over dx, but it's also equal to y prime. And so now when I take the second derivative, doing the same thing, Notice that there's another y prime in there, and I actually have notation of what y prime is, which is that negative y to the 1/3 divided by x to the 1/3. And so I can actually insert that in, and then I can that allows me to keep moving forward because you have y double prime and y prime in the same expression, it's hard to be able to move forward with those both in there. So that y prime, since we already know what it is, I can plug it back in, and that allows me to be able to like simplify a little bit more. Now once I've done the quotient rule with this one, because it was a fraction, I'm able to simplify a little bit, and that's all I'm kind of doing here. I noticed that there's some y's in those first terms that I can put together because of the exponents. They also have a y that you can factor out, but that's pretty much all I can do for this problem. And then that would be my final answer. Okay, thanks for watching.